get started. It's a real pleasure to have today our own Roger Blandford here. Roger doesn't require introduction, so I'm just going to sit down. But in fact, Roger was the founding director of CAIPAC in terms of local things, and came from Caltech to actually stand up CAIPAC, which clearly has been a very successful thing, and led, among other things, to increasing the size of the department in terms of faculty members by like a third or something. So that's, if nothing else, we become maybe the largest department of HNS. But Roger has, of course, a very large number of prizes and distinctions. I have to say, since I don't want to go through all this, but most of, or many of them, having the dubious name of royal in them, which you have to explain. And he's going to tell us about electrodynamics in extreme sort of conditions, and I think this is related to a substantial grant that is leading in many other institutions from the Simons Foundation. Roger.
Well, thank you very much, Giorgio, and thank you for coming. And thank you also to the Simons Foundation, who supported us. I think for us, collectively, to different places, we've been trying to put together a large collaboration like this. And this was probably about our sixth attempt in various forms or another. And this time it came through. And I'll tell you a bit more about what we're doing. And but mostly I want to discuss the science here. And and I'm going to do this in a way that I think often kind of irritates physicists, in that it's going to be sort of all over the place. There's this one thing here, one thing there, and it just seems like too many things that are coming up. And I've tried to organize it a little bit by the physics. And our actual collaboration is focused on electromagnetism and its extreme electrodynamics. So it's really taking electrodynamics and taking it to the limit, as it were, which we see as very much new territory, frontiers in physics, if you like. And so I'll tell you a little bit about that. And I'm personally interested in a lot of the science and actively working on it right now with many collaborators, some of whom are in this room. And I'm just going to focus on one of these topics probably in the last third of the talk. And I'll try and explain what's interesting about it, what's relevant about it, and where we are right now. So without further ado, let me just say a little bit about the Simons collaboration. This is an international collaboration, as you can see. These are people who all sort of basically know one another. We're all interested in this field, and we're interested in it from different perspectives. Most of us are theorists. There are some who are more observational, some who very much like doing computational astrophysics. In fact, that's probably the majority of the collaboration, which reflects the way people are working now. And some of us like doing more theory things, and it brings together these different aspects. And the topics I'm going to discuss about are actually focused on two very important astronomical sources, which are neutron stars and black holes, and I'll try and keep everything sort of anchored to the neutron stars and the black holes, but show you how they take electrodynamics into new territory. Oh, quite a couple of people here, some of whom I'm working with is Noemi Globus, who's somewhere here. There she is, she's in the audience, and she's been a collaborator on much of the work I do. Sasha Filipov is my deputy, and he's put an awful lot into this. He's the sort of my alter ego. He's very heavily into computational methods, and I've tried to do the more theory methods, so it's been a very nice complement and a lovely collaboration. Chris Thompson's been here as a visitor, as has Amy Levinson, a long-time collaborator. Anatoly Spikovsky was here as one of our first postdocs in CAIPAC. Yaji Yoon was a student here, as was Richard Anantua. Ke Fang was a postdoc here. and the rest have all been here in one form or another. So it's people who know one another, but have very different scientific perspectives. When we're making a lot of progress, I think, on sort of rationalizing them. We also have an advisory board, and I just show this because, for several reasons, Mina, you heard about a couple of weeks ago. She's on it. Phil Buxbaum is here, bringing very different experience to this. Federico Ferrusa was at SLAC, but has now moved to a very nice position in Lisbon. Vicky Caspi, I had come here to the colloquium a couple of years ago, and she's going to repeat as the Bunyan lecturer. I strongly advertise her talk. It's going to be highly related to this, and I backed off the thing, one of the topics that she's going to talk about, but I can't resist saying something about it. And so she'll be here next week, so please get to see her, and then the others of her people who I'm sure you all know. So let's move on. So let's start with neutron stars, and I'll say a little bit about the history first. So of course now they were actually discovered in 1962, but most people had not realized that. But in 1967 was when they really were discovered, and this was the first pulsars by Jocelyn Bell and Tony Hewish. And just as a personal note, the very first astronomy talk or science talk I ever heard was in the Cambridge University Astronomy Club as a first-year student, and it was given by Tony Hewish about pulsars that had just been discovered. So that's my first introduction in some sense to astronomy, and it's been spectacular since then. And I've got to know both of them, of course, very much since then. Jocelyn was here and as the Hofstadter lecturer last year, and did a truly splendid performance for us, and it was great seeing you here again. So that was the discovery of pulsars in 1967. There's a theme that's going to follow through this. This is discovery science all along. It's discovery science. It's not the sort of Calvinist view that is often practiced by the agencies and so on. This is really things where you're too stupid to know what's going to come next, and it's a great surprise. And this was a surprise too. And what happened here, and it will happen again, is that there were various ideas. People find these pulses from the sky, radio pulses, tick, 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 tick. Little green men, that was one of the explanations. That'll come through. Then there were modes on white dwarfs and so on. It wasn't a crazy idea. There were crazy ideas, but that wasn't the one. And then people thought more about it, and they observed more, and they ruled it out. And so then it became pretty clear that it was spinning magnetized neutron stars. And we'll see what a neutron star is in a moment, but it's a spinning magnetized neutron star, and these have turned out to be spectacular clocks, and not only are they interesting in their own right, they're extremely useful for physics and astronomy. And I'll just give a flavor of this. I can't do much more. In no particular order, here's a fast radio burst that happened about 15 years ago. We think is also a neutron star. The evidence for that is less compelling, but it's pretty good, and I'll say a bit more about that. Here are two neutron stars merging in a LIGO event, two neutron stars in 2017, and we see this is the signal from LIGO. I'm not going to say any more about that. This is obviously a spectacular thing for this, and leading to a lot behind that. Here are objects which are called not fast radio bursts, but gamma ray bursts. Gamma ray bursts, they were discovered in the 60s by satellites looking for illicit underground nuclear explosions, looking for the gamma rays from those, and instead what they found were sources outside the solar system. And there was a big debate at the time as to what they were. I'll say a bit more about that. But we now know that most of them are cosmologically distant, and also, of course, good probes of the universe. Here at the bottom here, they're seen as all sky here. The fast radio bursts. These happen about once a day. These happen about once a minute. So over the whole sky. So this is a very common phenomenon. Here's a soft gamma repeater, and this was an early observation of this.
The flashing thing is radio?
Yes, but you're seeing it in optical simulation. Yes. Maybe there's radio there. Well, I suppose there is. Yeah. Okay. Okay. So this is what is believed to be what is known to be a neutron star, and it's one with a relatively long period of about 5 seconds. and you see the pulsations here. This is in X-rays and gamma rays, and these were discovered about 20 years ago, and we've now got, I'll come to what the picture is here, what's going on, and they have these enormous explosions, we'll talk about it, and it was inferred that they were associated with neutron stars, but special ones, one that didn't have fields the mere strength of about 100 megatesla, but instead 3 orders of magnitude larger than that. So they have enormous magnetic fields. We'll come to that in a moment, and this was a sort of big discovery. We now know, of course, much more about this. So if we go on to the sort of theory of this, and here's a neutron star, and I've occasionally given talks on this sort of thing, and it has structure in it. It has a nuclear density, about 10 to the same density as atomic nuclei, essentially, a little bit more than that in its nucleus. The equation of state is an issue and not well known, and being measured by Roger Ramani and others. In their observations, there are magnetic fields associated with it, the superconductivity, superfluidity. We'll comment on that. They've got lots of structure you can see all the way through the crust, and we can see manifestations of this in the observations. Again, you'll see a little bit more of this and there. So there's an awful lot of physics there, and the talks I used to give it, would say there's essentially no area of physics that doesn't find some representation within a neutron star. There's a few, but not very many. Now, the magnetars themselves, I say 10 to the 15 Gauss. If you wanted it I thought meant to change this to SI units, but never mind. The magnetars, they have fields that's about 10 to the 15 Gauss. That's 100 gigatesla. And the key thing here is it's 30 times the quantum electrodynamical critical field, where the spacing of the Landau levels is equal to the rest mass of an electron. So it's 30 times larger than that, and what's going on in the interior is a matter of strong speculation and research at the moment, but it could be as high as 10 to the 100 times larger than that field that you see above the surface. That could well happen inside the neutron star. We don't know. It's an interesting possibility. And now the reason why you see pulsars is that if you just take the dipolar component of the field, they make beams of coherent radio emission which swing around like that, and you see those ticking once every rotation period. And you learn a lot from just doing that timing, and we'll talk more about that. So there's a lot going on there. And the real surfaces of neutron stars, well, I have to believe they're at least as complicated as what you see on the surface of the sun. And so it's going to look, this is actually a simulation, but it doesn't matter. It could be a cartoon. It's extremely complicated, and that has manifestations as well for what you observe. So if we'd ask what's been happening lately, and there's a lot going on right now, I can only just give you a small flavor of this. Looks like people are seeing oscillations associated with these neutron stars. These could well be astroseismology that you're beginning to see. This is all very new, so it's not a long-standing business. A lot has been happening with the timing. This is the famous pulsar in the Vela Nebula, and this is one that shows small, what are called glitches. These are change speed-ups followed by slowing down. We know much more about this, of course, and so here's a sort of regular succession of glitches from the past, but it's still going on, and we've learned a lot more about it. And this is telling us about cataclysmic events that happen inside, that's quakes, star quakes if you like, inside the neutron star. And there are various ideas, again, I haven't got time to go into them, with an origin in condensed matter physics that explain how these glitches occur. Here's something else that's happening. I said that there were merging neutron stars. They also create structures called jets, that is, relativistic outflows in anti-parallel directions. We'll see more of those in a moment. That was a discovery that was made. And then perhaps what is, I think, an underappreciated one, this is one that Roger Ramani, who's a member of the IXP team, an X-ray polarimetric experiment that recently has measured lots of things, but especially the linear polarization of the X-rays from the nebula surrounding the pulsar. And the point about this, and I can't explain in any more detail than this, but the conclusion you should draw from this is that the polarization is extremely high. And this nebula, on scales of light years, around the neutron star, is filled with a giant organized toroidal magnetic field. That means there's an enormous current flow flowing through this nebula that's powered by a spinning neutron star in the center acting as essentially a battery. That's, I think, and this is a message that's much larger than the Vela Nebula. That's my view at any rate. Okay, black holes now. So here's some history as well. This is the first quasar discovered by Martin Schmidt using radio positions by Cyril Hazard, and that we now know, at the time, there were many ideas that were floating around, including non-cosmological redshifts, funny stars, clusters of neutron stars, and so on and so forth. There were many ideas, but by the end of the 60s, and certainly by the end of the 70s, I think everyone has signed into the idea that quasars and active nuclei of galaxies, essentially every nucleus has an active center, and it's a massive black hole. In the case of our galaxy, it's a mere 4 million solar masses, as shown exquisitely by this crew, or two of them, and then we also see black holes in X-ray sources, binary X-ray sources. These are stellar mass black holes. This is the first one, Cygnus X1. The work was done in 1971 by two people I had the privilege of meeting. They were lecturers at a summer school I attended as a student, and I got to know them a bit. And this was the first sort of evidence that black holes existed in stellar systems. And it was really, there was a binary system, we knew what the masses were, and the masses were too heavy to be a neutron star. What else could it be but a black hole? So that was historical in the 1970s. Here's the Event Horizon Telescope image, that's wonderful. Here's somewhere here, you missed you will have seen, of course, the emerging black holes that have been the prime source for the LIGO Gravitational Wave Observatory. So that's sort of black hole physics in a serious way, and the whole show has garnered two sets of Nobel Prizes. I must admit, when I saw these pictures, of course I saw that one first, and then I saw that one afterwards, and then I was pleased to conclude that black holes have hair after all. Okay, black holes, this is the theory. I can hardly do justice to it. It was a heroic business in the 1970s figuring out, Roy Kerr, the event horizon. This is the event horizon of a black hole, and it's surrounded by this zone called the ergosphere. And inside the ergosphere, some sentient observer could be outside the horizon, but they would have to rotate. They're dragged around, if you like, by the space-time, and so they have to rotate around outside in this sort of bluish region here, and that's called the ergosphere. There are many other features of this. One of the important features to which I will return in a moment is that this black hole, when it spins, has an energy which you can associate with its rotation, just like a top or a neutron star, and that energy is there for the taking. It's extractable. It can be taken out and used to power cosmic sources. And one of my strongest take-home messages from this talk is that there's even more of that happening than we suspected. And this really is a source of a lot of the most luminous and powerful objects we see. So what we have in the traditional way of looking at these black holes as astrophysicists is they're surrounded by an accretion disk. And this accretion disk looks kind of warped here. It's gas that's orbiting the black hole like in Saturn's rings. But if you actually made an image of it, which we in principle are doing, and Dan Wilkinson explained to you about how to do this sort of thing using X-rays, then you would see something like this due to the bending of light and the distortion of the image. So this is all GR at work, if you like. The point for the astrophysics is if you want to know what the prime mover, the source of the power is for these amazing cosmic sources, if you want to know what that is, the conventional view is that it's gas that's spiraling inwards, releasing its gravitational binding energy through an accretion disk. And that's almost certainly going on in many or most of these sources, but I'm going to tell you a slightly different story. When I say that the black hole can release its spin energy, the way we think about doing this as a practical method for the universe at large, the way it's actually implemented, is using magnetic field. Hence, of course, my concern with electromagnetism, and those magnetic field lines thread the spinning black hole just like they would thread, in this case, a fair conductor with a resistance of about 100 ohms, and that would be held in place by orbiting gas. And then this magnetic field lines exert a torque which removes the rotational energy of the spinning black hole and powers the jets and perhaps much else besides. So, just to emphasize, the black hole is the astrophysical black hole is even simpler than an electron. It's just mass and spin that really characterize it, not even charge in this case. And there's gravity power and there's rotational power, and they're the source of the power that fuels its cosmic sources we can see right across the universe. So what's been happening more recently? Here are just some things. Here's the Event Horizon Telescope. There are jets, as I said, that are made for these. They stretch right out, and they almost certainly keep the gas outside the galaxy in warm and glowing. Here's the ring around the black hole, shown there, as predicted and observed spectacularly by the Event Horizon Telescope. And then here are the jets seen with increasing resolution, and it goes on and on. I didn't show you all of them, but the key thing I want you to take home is that what you're seeing from these jets is the emission comes from the walls, from the boundaries of the jet. We've got an outflow, and on the wall of that jet is where the emission appears to be coming from. That's an observational discovery. It was not unexpected, but it's very important to have it. Here's a thing called a tidal disruption event. There are lots of these going on. A minority of these make jets. And this is essentially what happens when a star gets too close to a massive black hole in the galactic nucleus. That releases a lot of energy suddenly, and then that makes these jets, we believe, in a few cases. Here's a galactic source called SS433. Again, something new happening there. This has been known since 1979. It's a black hole in a binary system, another star around it. This black hole makes a pair of jets. They precess in space, and this has been observed. We know a huge amount about the systems, a lot of observation. It's still a puzzle what's actually going on in any detail. But the new thing that's happened here is that they've discovered gamma rays from it at very high energy. So just like the just like the sources associated with quasars and so on, these are sources of very high energy gamma rays. Another thing that's going on is the neutrino business. If this makes TeV gamma rays, that means 10 to the 12th electron volts, sort of LHC type energies. This makes PeV energies 1,000 times larger, and they're seen as neutrinos. Now, the neutrino detectors are seeing sources of neutrinos that are almost certain. I don't think anybody really contests the fact that they're from outside the solar system. They're astronomical sources, but their identity is more contested. Many people believe they're associated with local, prominent astronomical objects. I'll count myself amongst the skeptics here, and I really don't believe that they're coming from local objects. I think they're coming from much more distant objects, because you can see neutrinos right across the universe. And I think you'll see more from the distant things, and it's really a background you're looking at. But we'll see. The point is, as you get more neutrinos, people won't be having this debate for very long. Here's cosmic rays. Cosmic rays are seen, obviously, in this room, passing through us as we sit here, and they extend in energies up to exaelectron volts. In November, the second highest energy cosmic ray was reported by the Telescope Array Collaboration, Japanese for sun goddess, and here's the shower that it produced, and it had an energy of 2 times 10 to the 20 electron volts. That's about 50 joules. That's a sort of fairly well-hit tennis ball. Okay? That's that energy in a single particle, probably a heavy nucleus. Think about that. So how does nature perform this trick? That's the puzzle. There's one more that's a bit higher energy. We know a lot more about them. We know there's a dipole there now, and so on. And then here's something again that's very recent. Last summer was announced that there's evidence that there's a background of gravitational radiation from the universe, and it's this gravitational radiation is in the nanohertz band. It's got periods of order a year, and it's seen from the timing of pulsars. The spinning magnetized neutron stars is what you detect it with. Here's the money plot, as it were, and it wasn't totally convincing, if you like, if you just looked at this, but there is floating around. Many of us have seen much better data that's coming out, and I'll just say that I wasn't really doubting it, but I don't doubt it at all now. And the thing that I do doubt, though, is that the putative source of these gravitational waves, the sort of complement of what LIGO sees, the putative source of these gamma ray gravitational waves is binary black holes. When galaxies merge, they've got massive black holes in their nuclei. The black holes are going to merge, and they're going to make gravitational waves. That is incontestable. And long ago, we sort of thought about these things, and I don't think there's any way of stopping that. However, the level that's reported, I believe, is too high, and I think it needs another source. And we're going to find out before very long whether another source is required, because there are going to be better measurements. But my guess is, I'll just cut to the chase, and I'm thinking about this a bit with Andrew Sullivan, who's here, is that it's really a cluster of black holes that makes more power in this way. But we'll see. This is all new stuff. People are having ideas. People are thinking about it. And then observations are favoring some and disfavoring others. I want to just go back, and this is a little bit of sort of science philosophy here, if you like. I want to go back to the gamma ray bursts and say what happened. Firstly, I told you where they came from, which was people looking for underground experiments, Ray Klebersdal and others in the 1960s, and then it was realized that they were cosmological objects. And then, as you might expect, there were lots and lots of theories for what was responsible for this. There were, in fact, one theorist got so frustrated with the business that he got a published paper listing all the published papers with different theories in it. There were well over 100. And one of our colleagues, Raoul Ruderman, said this, and sarcastically, but in a review which I attended, which was spot on in terms of the science, and there were all sorts of crazy things. We now know that essentially the gamma ray bursts as a class are three highly distinct types of object. On the one hand, they are magnetars, these with their intense flashes of gamma radiation. I've told you about that. There's another class that appear to be neutron star mergers, like the ones I just showed you. And the third class are a type of supernova explosion of a massive star that makes both of these will make black holes, but that makes a black hole directly, and makes a black hole and both of these make jets. Both of these types make jets, and so this is a sort of a minority, but probably a large minority of regular supernova explosions also make these powerful flashes of gamma rays. And they're basically associated with jets that are made by the central black holes that push their way out of the collapsing star. This is too incredible to believe, but there's really no alternative to that explanation. It is truly extraordinary. This is what happens. And the point is that there were lots and lots of ideas, most of them pretty crazy, but not all. And then we've sort of, observations have essentially led us to a very clear understanding of what is at stake and what is going on, and of course raise more theory questions. The fast radio bursts, and this is what Vicky Caspi is going to talk about next week, and I don't want to steal her thunder, but I will say some more about this. I sort of de-emphasize this here, but it's the same sort of story. Is that when these, these were been around for about 15 years, and these were the sort of explanations that are out there. I won't read them. The one that I will read was that there was an astronomical discovery that they happened at lunchtime. And this turned out to be a microwave oven. You have to be a card-carrying radio astronomer to know how embarrassing that is. Okay, so, but they were called peritons, and people can recognize them now. They don't take the data at lunchtime. Okay, so, but nonetheless, there are real things there, and alien light sails, if you like that sort of thing, and all this sort of stuff. This is silly. This is not so silly. That is probably still going on in many of these, and this is what people now believe on the basis of this recent observational evidence. The association of one of these soft gamma repeaters, of which I've just shown you, associated with a magnetar, associated with a low power fast radio burst, and by extension, it's believed that many of these fast radio bursts, these flashes of radio emission that happen about once a minute, just radio emission, pulse, 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 pulse. We'll say a bit more about those later. Those flashes of radio emission, you see them across the universe. They're cosmologically distant, and they're associated with many of them associated with magnetars. But I'll bet that not all of them are. There are a few other things probably going on as well. So this is all exciting time. It's all pretty new, all of this. So let me just go on. I'm going to, in the abstract, I sort of said these as extremes. So I'm going to tell you about the extremes here. And sort of where I come from a little bit is as a child, I grew up seeing advertisements for a beer, which you may have heard of, called Guinness. And they had lots of advertisements like this. And they also, in response to the desire to have some authoritative source to resolve arguments that took place in public houses while people were drinking their Guinness, they produced the Guinness Book of World Records, which you may have heard about. Certainly the people in GPB have, because they have an entry in it. And so it's in that spirit that I sort of show you the extremes of astrophysics.
Same Guinness.
Sorry?
Same Guinness, I didn't realize.
Yes, oh yes, absolutely. It was an engineer who thought up the idea of doing this. Yeah, one of their, yeah. Okay, so here's the black hole mergers, 10 to the 49 watts. Okay, a 1,000th of c to the 5th over g, if the gravitational power. Gamma ray bursts, 10 to the 26 watts, but this is a stellar object. And the active galactic nuclei go up to about 10 to the 37 watts. These are enormously powerful. Only black holes and neutron stars have the power supplies to satisfy this. If we go to the energy frontier, I've already mentioned the neutrinos. This is a facility called IceCube. There are other ones. Energy is now measured above a petaelectron volts of cosmic origin. Where do they come from? The cosmic ray gamma ray. Whoops, this has gone. Yeah, these are the gamma rays. They're almost as energetic. Now, this is a facility which I've actually visited in Western China, in Western Sichuan, called LASSO. That's finding very high energy gamma rays. And it's extraordinary, and they're a real challenge to explain them. Here is cosmic rays. As I said, they go up to energies. There are two facilities really active now. One's called Auger, the other's called the Telescope Array in Utah, and they're measuring cosmic rays and learning about their spectrum, their composition, and so on. It's a long business. They don't hit the Earth very often, but they're measured, and explaining them is where to go. So this is the energy frontier. I want to take the thermal frontier. Here is the interior of a neutron star. I said there was superconductivity and superfluidity there. The critical temperature, which is achieved when they're about a second or so old, is about 10 gigakelvin, 10 to the 10. I think this counts as high TC. 10 to the 10 Kelvin, so this is at nuclear densities, of course, and of course there's a huge amount of physics there, most of it stolen or borrowed from condensed matter physics. And then if something I put in the abstract, if you ask what the effective temperature, which is conserved along a ray, of the radio waves that are seen from the fast radio bursts, these are the fast radio bursts, it gets as high as 10 to the 40 degrees Kelvin. I'll come back to that point. 10 to the 40 degrees Kelvin. That's hot. Okay, astrophysics has been transformed by what is now called the multi-messenger approach. I was actually present at the coining of that word 25 years ago, but it takes that long for it to catch on. And basically the thought is that if you might be an optical astronomer looking at one octave, there's all of this from radio waves to gamma rays, there's gravitational radiation, cosmic rays, neutrinos, and so on. There's 140 octaves or thereabouts. Then astronomers are using this all the time rather than just what their eyes might show them. And this is completely changed our view of the universe and its contents. So zep2 electron volts to zeta electron volts, if you like. So there's an observational frontier. There's a huge amount going on in terms of observations, which is really driving this business. It's really an experimental observational business. Here's Webb Telescope. Here's, I mentioned IXP, Romani IceCube mentioned that. Here's Vera Rubin Observatory, which is coming online and camera being built at SLAC. Here's what Vicky will tell you about. This is a facility for measuring fast radio bursts. It's actually there. It's called CHIME. It's for doing cosmology, but the people doing time domain astronomy have latched onto this, and they're building an even larger facility, as are people at Caltech building a DSA 2000 facility. These are going to be coming online fairly soon, and they're going to again transform this type of time domain astronomy. Here's LASSO I mentioned. Here's a new X-ray telescope called CRISM, which has just started producing results which are very exciting. Here's upgrade plans for cosmic rays, and here's an upcoming Chinese space mission, Chinese and other space mission that will transform gamma ray astronomy. There's a cosmological frontier. All of this, of course, when you see these things at large distances in many different ways. Here are the active galactic nuclei. These are not sort of quiet little sideshows in the middle of galaxies. They produce maybe 1,000 times as much power as the surrounding galaxies, and they have an enormous impact on their environments. And so they are big players in the life of the universe. Then if we look at the so-called kilonovae, this is a phrase that was actually coined by Vahid Petrosian, who's here, which is the aftermath of the merging neutron stars, and make a lot of the heavy elements. Again, I'm not going to explain any of this. It's there. The fast radio bursts, I've said, you'll hear more about this, and I deliberately showed a very old slide here, so you'll get an up-to-date version of this next week. These measure the baryons in the universe. They're doing cosmology. And then, of course, we've seen this new background, the gravitational wave background, and this is being detected by pulsars. That's out there. That's a significant part of the story of the universe. That's cosmology. There's a horizon frontier. It seems oxymoronic, but I think it's okay. Basically, you can't see too far in certain types of the spectrum. If you take the gamma rays and you go up to sort of nearly PeV energies, you can't see very far at all, because another photon interacting with a gamma ray makes an electron-positron pair. There's an inescapable opacity there. And why this has become interesting is that the best of all time gamma ray burst, which people in Fermi, the Gamma Ray Space Telescope that Peter Michelson led, people using that have, the LASSO people have claimed to see a gamma ray that's pushing up right against the infrared background that should come from stars. In fact, it really transcends it. And if you believe QED, which I do, then it's got to be an overestimate of the energy. So this is becoming very important for cosmology, if you like. And then the cosmic rays, there's a limit to how far you can see them. The highest energy ones have to have local sources. There's no escape from that. So this again is a sort of, if you like, a frontier. And then what is transforming, I think, the theory of this business is computation. And there are various approaches to doing computation to try and address the genuine physics problems that are associated with these, with the models of these sources. And I'm going to not do any justice to what's actually been accomplished. One is to use fluid-type methods, but of course including magnetic fields, because they're everywhere. So there's magnetic field in there, not just fluid mechanics. It's a plasma, conducting plasma. Then you do kinetic theory, and that means you put in the motions of the individual particles using particle-in-cell methods, they're called. These are just individual particles that are moving around. Obviously, your dynamic range is much less, but you've learned a lot from both of these techniques and trying to join them together. And then for stuff going on inside the neutron star, under the surface of the neutron star, you use the techniques of molecular dynamics. And now the game is they've been done essentially with unmagnetized neutron star matter. Now is to add the magnetic fields. That's what people are doing. Here, I'm not even going to start to explain what's going on in these simulations. There are countless movies and results. But the point is, it's not just making shows. You're really learning the answers. Serious physics questions are being addressed by doing these simulations. This is a neutron star and a wind rotor. Notice this, and then here's something associated. That's actually a neutron star too. This is a boundary layer, like the sort associated with the jets and so on. And here's something going on beneath the surface of the neutron star. There's countless other examples. It's a frontier. And then finally is an experimental frontier. There are facilities, light sources. They are getting into this super Schwinger regime sometime in the not so distant future. They're not yet. And Phil Buxbaum and others, and Sebastian Murin and Federico Fuse, who were here, are very much involved in this, and there are facilities going on and schemes for getting to higher energy densities and effectively getting into this extreme electrodynamics regime. Now, of course, this is a physics colloquium, so there's a physics frontier here, and I'm just going to show this without any explanation. There are the four famous forces of physics. They all find big representation in this business. I'm not going to deconstruct this or anything, just show you it's all there. But the thing that really does have to be added, in some sense, the coupling between all of these four expressions of physics is plasma physics. Plasma physics is the collective interaction of charged particles, high or low densities, doesn't matter. It's always subtle, always complicated, and that's where the computation is teaching us so much. So let's get back to electromagnetism. This is the electromagnetic frontier. I've shown these two pictures before, and let me just emphasize here that the 2 points that I made, one is the neutron star magnetic fields. The regular ones are about 10 to the 12th Gauss. The super ones, called the magnetars, are 10 to the 15 Gauss, or 10 to the 11 Tesla if you prefer. And the interiors may be yet 100 times more than that, we don't know. And then the spinning black holes, I didn't emphasize this, I didn't say this before, but I'll say it now. If we've got a spinning black hole, it's a spinning conductor. That means you're generating an EMF. Anybody who's done a little bit of electromagnetism will know how you do that. You've got an omega, you've got a flux, therefore you've got an EMF. For M87, this is the Event Horizon Telescope orange ring in the newspapers. That is 10 to the 19 volts is the voltage you're making. If you take a quasar, it'll be something, a regular quasar will be about 10 times larger than that, and so the powers are the square of that. And the gamma ray bursts and the magnetars are arguably 100 times more than that, 10 to the 23 volts. And the currents associated with this are 10 to the 21 amps. Those are the extremes. Okay? So that's the territory we are going. Now, I'm not going to say that this is new physics is going to be required all the time. I think all of us are eager to find new physics, but there's no compelling evidence that we need anything other than classical electromagnetism, which is here, or quantum electrodynamics we'll come to in a moment. But if you are going to find any, this is the territory to look. This is where to look. Okay, so classical electromagnetism. Here's, of course, Faraday, Maxwell, and you know this. These are in units in which pi is set helpfully to a quarter, and you know the story of this. And the point I want to make here, and I'll come back to this point, is that when Maxwell wrote his treatise in the 1860s and then his papers, in the 1860s and then developed his treatise, then he thought about electrical current as continuous. It wasn't until almost 1890 that particles entered with the discovery of the electron, and the Lorentz force came. There was some things that were not quite right that were said before then, and it's because the Lorentz force after Heaviside, who was the first person to understand this properly, and then of course from that went atomic, nuclear, particle and plasma physics that came from that. But where the start of this business, in the 1860s, was really electrical current was continuous, like a description of a fluid. And of course we use all of this. Here's two astronomical objects, Van Allen belts, there's all the stuff that's going on in the sun and so on. And this is classical electrodynamics. We've no reason to doubt it, but we're taking it into new territory. We're taking it into, how are we doing for time? Okay, we're taking it into very different territory, with particularly around general relativity and so on. We think we know how to apply it in general relativity, but it sure would be nice to find confirmations of that, and so far we have that. If we consider the same exercise in quantum electrodynamics, it's extremely well tested, like classical electrodynamics, and we're now in the regime where magnetar fields at least as high as 30 times the so-called Schwinger field. This is where sort of the spacing of the Landau levels is equal to the rest mass of an electron. We're well above that, and so you need new techniques, and in particular you have to handle the many-body plasma-like processes that are going on there, and we've got a huge amount of effort in our collaboration with people building codes to perform these experiments, and it's a very exciting business. We're learning a lot from it. So I just summarized what I've said. These are just sort of a list of research areas: neutron star magnetospheres, interiors, understanding the phenomenology, connecting all of this theory to the observations that are coming from the telescopes. We're learning a lot from that, and we want to make those connections, that phenomenological connection. It's no good just solving abstract problems if it doesn't relate to the observations. Similarly, for the black holes, I showed you some of these jets. We do not know quite how they form. I'll say more about that in a moment. They're associated with orbiting disks. They're associated with outflowing winds. And we have got a sort of rudimentary understanding of what's going on. We sure would like to have a better theory like that associated with stars, for example, or indeed galaxies, where we have a better idea of the actual physics that's going on that's well corroborated by observations. Not there yet. Then there's the possibility of testing, say, GR near the event horizon. You've got to understand these physics if you want to do experimental tests of general relativity in the strong field regime, not the weak field regime that's probed in the solar system, but the strong field regime. You've got to understand how the magnetic fields behave there, and there's a lot going on. And then again, there's the phenomenology. These disks are extremely active. They have coronae. There are boundary layers on the jets. There are current sheets all over the place that are doing the emission. All of this is being investigated by my colleagues and many others around the world. And it's very exciting, and just to try and make those connections. There's a lot to connect to in terms of observations. So now I'm going to sort of segue into the last part of the talk. I'm going to just take one of the things that I personally am interested in. I'm going to explain what the issue is. I'm going to editorialize. I've probably done a bit of that already, but I'm going to editorialize a little bit more and tell you what I think is actually going on. And I've been right about some of these things, and I've been wrong. I was wrong about the gamma ray bursts. I thought they were local neutron stars, most of them. But I was there at the meeting where the distribution was announced, and within a day it was blindingly obvious that they were cosmological objects. So I was wrong. Okay, my thesis was written on clusters of neutron stars. That is my advisor's idea. But it is clusters of neutron stars making active galactic nuclei. No one believes that anymore. But the FRBs, I think I got that one right, and several of the other ones. So maybe it's right, maybe it's wrong. But this is work that I've been doing, particularly with, as I said, with Naomi Globus, who's sitting in the audience. And I'm going to connect it to the well-known observations of the M87 black hole. Been much publicized and so on, and it's been a great accomplishment. So basically, I'm going to say there's 4 big observational puzzles, and I'm somebody who works from the top down, from the observations, and try and infer what's going on and then simulate it, rather than start from the simulation and compare with the observations. These are 2 approaches, they're all good, but I will take the first one. So we know we can measure the mass of it, and it's been corroborated. It's about 6 billion solar masses. That means the period of something that was orbiting close by, the characteristic timescale of that, would be about 7 days. And the rotational energy is enormous, and it's enough to keep everything that's going on around it. The rotational energy is enough to keep everything going on around it for 1 trillion years, much older than the age of the universe. So where does this energy go? Well, the most powerful thing in this source is the jets. Not what they're looking at with the Event Horizon Telescope, it's the jets. And when I was a postdoc, my colleague Jerry Ostreicher, it was the time of Watergate, and everyone was saying, follow the money, follow the money, follow the money. And he used to say, yeah, all true, but follow the energy too, and that's the way you understand astrophysics. So following the energy is a very good rule. And with the power of the jets is at least this, and probably, I would say probably larger than this, and basically it's 100 times more than what you see with the telescopes from the surrounding gas. So you're making power for these jets by this electromagnetic process, and it's most of the power in the system. And so the question for me is, why is the ring so dim? And there are various ways of expressing this, but it's, for me, from the first time I saw the observations, this was the big puzzle.
Sorry, where does that number, the 6 times 10 to the 36 watts?
Oh, that comes from, you see these jets squirting out, 2 of them, in opposite direction, and then you measure the physical conditions at a safe distance to say how much power is there. On average, it must be more than this, but at contemporary, it's about that value. And some would say a bit more, some would say a bit less, but it's not wildly different. So, there's a mass, so the third puzzle is there's mass applied to this. There's gas that's falling in all the time. And we've got measurements of that. It's not as solid as the jets, I think, but it's a pretty good indication, and we'll learn a lot more from Webb telescope. It's about 10 to the 22 kilograms per second, and yet the models that are used by the Event Horizon Telescope and everyone else have orders of magnitude less power coming in. So it's okay to have power falling onto the disk surrounding the black hole, but if you want to get rid of most of it in a steady state, you've got to have some power source to do that. And the fourth thing is, if you look at these jets here, and these are some other examples from observations, you can see that they're being focused as they go outward. They're not spraying out like that, they're being focused. Something is focusing them, something is squeezing them in. And that is a huge clue, at least for some of us. And so there's jet collimation happening far away from the black hole. What causes this? So I'll cut to the chase and say what we think is going on. And that is, if I take this from the outside in, basically this is a sort of schematic. It's not a huge simulation, it's just a schematic. Gas falls inwards from all directions onto the center of the M87 galaxy. It falls in like that, and it forms a disk in orbit around the black hole at about 1 million times the size of the black hole. 1 million times, might call it a gravitational radius or a Schwarzschild radius. It's the size of the black hole, GM over c squared. 1 million times, that is when the gas sort of falls in. Then it falls down here, and then the contention is that what actually happens is that essentially all of this gas is blown away. Not by its own gravitational energy. It can't do that. It hasn't got enough energy to do that. The energy is coming from the same place that the jet power is coming from the spinning black hole. So the contention is that there's a flow of energy and angular momentum outwards into a disk, which instead of being, for the astronomers here, an accretion disk, is called an ejection disk. It's blowing stuff away. So we've got power that's added to this disk, and most of the gas that's supplied to the black hole never gets very close to the black hole. It gets blown away. There's some big cycle going on. And there are various ways that we thought about of doing this. I won't go into the details here. But the key thing about this story is that the magnetic field in the center is larger than is traditionally assumed in these models. It's probably several hundred Gauss, or something like 20 or 30 millitesla. And that field means that the particles that are emitting the electrons that are seen cool very fast. That's the thing that you know accurately. They have to cool very fast. So the model of what you're looking at with those big orange rings is a series of rapidly cooling flashes, flares, if you like, magnetic reconnection events. These are what must be going on in this picture, not the not a continuous steady, like the surface of the sun or something. It's not continuous emission. It's something that's lots of little flashes and so on. I'll come back to that in a moment. And so what we're really saying is that M87 is powered by rotational energy, not gravitational energy. And this is very, very different from the standard viewpoint. It may be wrong, but it's different for sure. And if you like, you say this is nature, not nurture. If you think about it, that's what it's basically saying. And it's a little bit like I use an analogy, a bit presumptuous maybe. We take the sun. In the 19th century, the sun was powered by gravitational energy. There were nice models of it and so on. And then the sun turned out to be 1,000 times older than that would allow. And so they had to invent nuclear physics to explain it. And nuclear physics has done very well, and much else that follows from that has done very well. And so we're saying that just like happened with the sun, the main source of the power in an object like this is in fact the rotational energy of the whole, not the ion energy. Now, so let me go on. Now I'd like to sort of take this into an electrodynamic realm. This is going to seem like a slightly rambling route, but it'll all come together at the end. What I'd like to do is to return to those Maxwell equations, which you've seen on a t-shirt or whatever, and if we just add one thing to them, which is that rho E plus J cross B vanishes. The electromagnetic force density, however you want to express it, vanishes. That says there's no inertia there. The plasma is irrelevant dynamically. Its only job is to supply electrical charge and current. And so what this does is, I'm sure, well, obviously E dot B is 0, but it leads to a very different form of electromagnetism that is perfectly evolutionary in an applied mathematical sense, and you can describe the equations of evolution, things like this or like that, and solve problems where you have no inertia. It's a limit where there's no inertia, if you like. It's called force-free electrodynamics. And the contention is that this is what is going on in these systems. However, when I said this was evolutionary, that was only up to a point. Something that you can show, it's been known for some time, but its importance, I think, has only been recognized comparatively recently, is that when you get to the point where the Lorentz invariant B squared minus E squared changes sign, then the equations stop being evolutionary. And so the big electromagnetic, electrodynamical question is, what then? What happens next? Now, the standard view is that you get a huge flat shower making gamma rays and electron-positron pairs and so on, and it's just sort of hugely dissipative. My view is really rather different. And what I think happens then is you make a transition to a form of electromagnetic turbulence. It's like water going down a pipe, and so when it exceeds its critical Reynolds number, you get a form of electromagnetic turbulence. And you make these long wavelengths, highly irregular, turbulent magnetic fields, and this happens without the production. It doesn't need the microphysics. To use a metaphor, if you were an oceanographer, you would, and considering an ocean wave, for example, you do not care about the private lives of water molecules. You don't even care about viscosity. It's not part of what you do. If you're an aerodynamicist, you don't care about it. It's all continuum mechanics. And if you take a tsunami, its brightness temperature, by the same rules I just gave for the fast radio burst, is about 10 to the 40 degrees Kelvin. Oceanographers don't boast about that. It's not part of their way of thinking about it. So the point is QED is so important in some sense you can ignore it. You can always supply the charges and so on, and this really is an exercise in continuum electrodynamics when you get into this regime, and that has interesting implications. I won't have time to go through with this because I think I'm running out of time, so let me skip this slide. Just say that this is just an exposition, if you like, of how you actually extract the energy from the spin of the black hole. Some interesting physics in that, but I'm not going to go through that. What I will do is say that when there's an electric zone, and this electric zone will happen when inside that region close to the event horizon, which we call the ergosphere. You remember that slide where I said there was that ergosphere, that region that where you had to be spinning? If you have magnetic field lines going through that region, then the magnetic field lines have to be carried around, just like a sentient observer would have to be carried around by the spin of the black hole. But that can't happen if they're losing energy and angular momentum, as they will be. So they need a source of power. And what happens in this version, what happens is that when you get to this E equals B limit, then you make lots and lots of turbulence, and it's launched on backward going orbits, which, as Penrose first showed, have negative energy, and so you're adding negative energy to the black hole, you're extracting energy from it. And so the field lines going through the ergosphere are also taking energy out of the spin of the black hole, as well as those going through the black hole itself. And this is a very different view from the standard one, which has a current sheet there in the equatorial plane, and this is, and then the field lines will do that. In our case, the field lines go through like that because we have this extra mechanism for supplying it constantly with energy. Now this is a theory, but I think it has three observational implications. And I just want to advertise these here. The first is, and it's in some sense already it's already been happened, but it will happen in much more detail, is a linear polarization. The field lines have to be vertical. That tells you about the polarization, linear polarization. And this seems to be what's observed. There also is a circular polarization. There should be a constant sign in this story. There should be a constant sign to the magnetic field because it's determined by the magnetic field at large distance, not some local dynamo or whatever. Again, that seems to be corroborated by the observations. And then the third one, which is very interesting, I know people in SIDP have been interested in this, is that they've been thinking about measuring photon rings and so on, which is going to be extremely hard to do using very long baseline interferometry in space. It's not impossible, but it's going to take a long time. Much easier is to think about the caustic structure around a black hole. If we take pencils of rays, backwardly propagating from the observer around the black hole, then they will make caustics, just like in regular optics. And that caustic will be these ribbon-like things. It wraps around the black hole, and it has this sort of asteroid-type cross-section. And if one of those flares were to cross like that, then it will produce a structure like this. Now, of course, it'll be much more complicated because you'll be a lot of background and so on. But it's worth looking in the existing months and months of radio data for structures like this. And that's the thing proposed to do. Okay? I'm running out of time, but let me just sort of say, Vicky will talk about this next time, the same ideas, the same notion of same question of what happens when you get into an electric zone. When E becomes greater than B, what happens when you get into that regime? Comes up big time in magnetars. So here's a story of what we think happens with those fast radio bursts. There's a starquake. I follow Aristotle as a physicist. And so there's a starquake. There's a magnetic wave as the magnetic disturbance goes down the magnetic 1 over r cubed magnetic dipolar magnetic field. It just gets, it's like a cracking a whip. There's a huge amount of lightning there, electrical currents all over the place, and then you're going to make these electromagnetic tsunamis. The waves are going to become linear, going to become make these tsunamis. So that's the sort of big picture. If you look at them, the waves become nonlinear. You can also have waves interact. Again, I won't go through this, but generically you make these electric zones. And my contention, which is different from those of other people who are thinking about this, and it's knowable which of these is right. This can also lead to electromagnetic turbulence, and those turbulent wave modes, force-free wave modes, going out into the magnetosphere, convert to electromagnetic waves, which propagate across the universe for the gratification of radio astronomers and everyone else. So they go right across the universe. And that's the contention here. There are many other models there. One of these will probably be shown to be correct. This makes it an exciting time to be in this business. And so here's my summary. I'll just say a little bit about this. I really ought to wrap up, but there have been remarkable observational discoveries, and they're happening right now. There are things happening in very short order where we're going to learn a lot more on the timescale of years, not on the timescale of decades. They mostly involve neutron stars and black holes. They're the Guinness Book of World Records. Here, there's all these objects which I've mentioned, and you must be thoroughly confused by the names and so on. There are opportunities here, surely, for discovering new fundamental physics in these regimes, and axions is one of the ones we're thinking about. It's possible. But there's nothing so far in the observations to indicate you have to have it. There are many explanations, but new facilities, as has always happened in the cases, will lead to very few explanations and new theory challenges that are much more specific. And all of these four wings, if you like, observation, experiment from the lab, simulation and theory are all contributing, and it's and, you know, there's a contrast in some sense between bottom-up and top-down approaches to the science. Both are valuable, and I don't know where this is leading, but it's certainly exciting, and I feel very lucky to be around here. And I also feel grateful to the Simons Foundation and all of my colleagues here for supporting this endeavor. Thank you very much indeed.
Thanks, Roger, for this very broad talk that span many orders of magnitude. Questions?
So could you elaborate how you produce this 10 to the 40 K temperature, which is like 10 to the 8 Planck masses?
Yes, you're thinking about it, everyone's thinking about it wrong as a temperature. You could ask an oceanographer that question. How come you've got something with an energy per unit volume of phase space that's 10 to the 40 degrees. So it's just not the right way to think about it. The point is you're dealing with continuum electromagnetism, not something that's trying to be a thermal process.
So what did you call the temperature?
Sorry?
Why did you call it a temperature?
I don't like calling it a temperature. This is what the radio astronomers say. This is what the radio astronomers keep on saying. They say, look, we've got the biggest temperature. It's 10 to the 40 degrees. They say that. And I think that, you know, and I say, well, an oceanographer doesn't say that. Why should you? I mean, you're clearly dealing with something. But, I mean, there's a more serious physics point there. The competing theories, and I worked on both of these, so I'm guilty as charged. The two competing theories are that you make what's called an antenna mechanism, where you make a bunch of electrons and positrons. You make a bunch of them, say 10 to the 20 of them, all acting like a giant electron, and reading Jackson's textbook and figuring out what the vector potential is in the far field and so on. That's one type of mechanism. The other is a maser. So you have what is effectively an inverted population of particles, easy enough to do. You start off with a little wave and it grows exponentially till it's 10 to the 40 degrees. Those are particle-based explanations. They may turn out to be right, and most effort has been invested in that. And just looking at Bob here, something I meant to say earlier, that Bob was one of the people in the two people actually, Bob and also Peter Sturrock, who may well be on this call, were two of the people who in the late 1960s, early 1970s clarified what's going on in pulsars for this particular story, and they were both great contributions, and Peter Sturrock is going to be 100 on March the 20th.
Bob.
So, Roger, so you've made my head spin.
Good.
Now look, so I think you said in one sentence, my distillation is, in the sky there are new collective effects that are happening with matter that's hot that you think are described by microscopic physics that we understand. Nothing, okay? But are nonetheless new collective things. Now, is that an incorrect distillation?
If your reductionist view goes as far as independent particle interactions, then I think I'm probably going to say that's the working hypothesis, and I see no evidence to contradict it. But there could be things like axions like there, which could be part of the mix.
Understood. Okay. Now, how many qualitatively new collective things the matter does are we talking here? 5, 10, 100? That's why my head is spinning. So you're talking about engines, for example, but there's nothing
It's
new about
science.
Engines are engines.
I mean, it's science. You can subdivide it. You can say there's only one field, which is condensed matter physics, and there's just the problems of condensed matter physics. It's all one collective thing, but that would be a total misrepresentation of what's going on. There's so many different aspects to it. So I can say neutron stars and black holes. I can make it 2.
Let me be very specific.
Yes.
Is the jet problem solved or not?
The jet problem is partially solved. It's a work in progress. Now, I'll give you the history there. And this is my contention. No, okay, we'll get to that. I saw the moving arms. That's great. So let me explain. Historically, the jets came from things that weren't even black holes. Then they came from accretion disks. Then they came from things that were going on associated with accretion disks that were outside. Now, most people, I think it's fair to say, accept the fact that they are powered. The power for them comes from the spin of the black hole. Okay? Not everyone, but most people do. Then the question is, how do you act? The second order thing is, you've got the power right. How do you then, it's like the sun, how do you get this thing out? And the observational discovery is that there's something that's collimating them. It's 2 forms. One is you actually see the walls, which many of us think is actually it could be a boundary layer, a fluid phenomenon, or it could be a current sheet, which is an electrical phenomenon. Either of those 2 are possible, and it's probably both of them at some level. Then you see those walls being collimated. And what's happening there, in this interpretation, is that there is a wind, like the solar wind, but much more powerful, leaving the surface of the disk containing magnetic field. So here's a black hole, here's an accretion disk, and here are magnetic field lines poking out of the surface of the black hole. So they're going to fling out gas centrifugally. They're going around in Keplerian speed like that, and they're going to fling out gas like that. But magnetic field, as you well know, has tension. So when those field lines get wrapped around the jet, as they will do before too long, then that tension, as you so ably demonstrated, is going to tug in and push on the jet and provide that collimation that you observe. So that's the story. It could be something else that's happening, but that's the story.
I think that was yes.
Yeah. Sorry, I should have given a shorter answer.
So Roger, thanks for this great talk. I'm curious about your M87 explanation. I would naively think that if magnetic reconnection is constantly happening, M87 would look much more variable than it is. So why, like, or I guess my question is, on what time scale do you think that is happening?
Oh, M87 is variable. In fact, there was a paper they made a great hoopla about recently which showed variations, not huge ones. And I would say that the interpretation that Noemi Globus and I have worked on is actually better attuned to a quasi-steady phenomenon, particularly as far as the magnetic field is concerned. Because remember, the sign of the magnetic field, the polarity, is determined by what's happening 1,000,000 times the gravitational radius. It's stable. Most of the models, which of course are the simulations doing their thing because they can do the thing in a small box, so that's what they do, have dynamos going on that are reversing all of the time, like in the Earth or the Sun. They have dynamos reversing all the time. Okay? And so they would be changing the sign of the circular polarization, for example, which has been rock solid in our galactic center for 30 years. And it should have reversed many times if those were the right models. And it hasn't. It's always been constant. So I would say it really is a more stable structure than the ones that have the magnetic field originating very close to the black hole.
Okay. One more question, one last question. Sorry. Yes.
So you say that the rotation is powered as on disk, and like a lot of power going out. Where did all the rotational energy come to the black hole in the first place? Is there, like, is it well understood where the rotational energy was built up?
Yeah, very good question. Does this happen in every black hole, in every active galactic nucleus? No, that cannot be the place. Black holes have got to grow, they've got to be fed, they need food, they're going to have that. So it's, in some parts of their lives, they are behaving as rotational powered objects. In others, they're going to be gravitationally powered objects. That, I think, is inevitable. So where does the spin come from? Well, think about gas. Just think about gas falling into the black hole from a significant distance. It's got more angular momentum per unit mass than the black hole has. Therefore, you only have to increase the mass of the black hole by a fraction, a small fraction, to spin it up to its maximal rotation. There's a maximal speed of rotation beyond which you can't spin it up anymore, for reasons that are well understood, and you get there pretty fast. So there are many stories that are told about the life cycles of black holes in the nuclei of galaxies, and some of them may well turn out to be right. But usually they have them spinning up and slowing down very often in the timescale it takes to double their mass. And to get up to the largest black holes are about 20 billion solar masses. That's a lot of mass that's got to come in. Those were, even M87, it may look not like much, but it was brighter than Vega in the sky when it was in its prime. But we're all like that. Okay, thank you.
All right, thank you. Thanks again.
Thank you.
About